Okay, the next thing I want to do is look a little bit more detail at set theory. We've been using set theory informally, and we will continue to use it rather informally, but it helps to get a sense for what set theory is so you can understand why we use it the way we do. So in set theory, a set is a collection of objects, and those objects can be anything. They can be individuals, they can be ordered pairs of individuals, they can be ordered triples, they can be sets of individuals, they can be sets of sets of sets of individuals. You can have any kind of a thing inside of a set. And set theory itself allows us to mix all different kinds of things. Here we have a set that contains an individual, A, an ordered pair of individuals, AB, an ordered triple of individuals, BBC, and a set containing AB. Although set theory allows us to do that, semantics has no use for these mixed sets. Semantics only uses uniform sets. In the interpretation of smile, the denotation of smile, we said that was going to be a set of individuals. All of the things in here are individuals. We have A, that's one individual. We have B, another individual. We have C, another individual. We don't have ordered pairs. We don't have sets inside of here, just individuals. They're uniform. And similarly for the denotation of C, here we're going to put in sets of ordered pairs. This is an ordered pair where the first one, A, sees the second one, B. Ordered pair AC, ordered pair BC. These are all ordered pairs where the first member of the pair sees the second. Uniform sets. We're going to use this symbol here, looks like a kind of curvy long E, to show set membership. So in set theory, we will have formulas like this. And we're going to read them like this. Here it says A, individual A, is a member of the set containing A. Or here, the individual A is a member of the set containing the individuals A, C, and D. Same thing applies to ordered pairs. The ordered pair AC is a member of the set containing the ordered pairs AB and AC. Another way to say that is if we look inside of this set, we're going to find inside it this pair. This ordered pair is right there. That makes it the case that this ordered pair is a member of this set. Now, a set is defined entirely by its members. We can say the set ABC, and the only thing that matters is that A is in that set, B is in that set, C is in that set, and nothing else is in that set. Now, a set can be thought of kind of like a box. You can put an object in a box. You can put an apple in a box, okay? But you can't put the same apple in a box, in the same box, twice at the same time. Similarly, you can't have the same apple in a single set twice. It's either there or it's not. It's not there a certain number of times. So while the set containing A, B, and C is a perfectly fine set, This is not. It's not because it has a single element, A, put in there 2 times. That's not something you can do in a set. Now, because sets are defined by their members, the only thing that counts is what things are in the set and what things are not. The order in which we write the elements doesn't matter. I can say the set containing A, B, C, and I can put those elements in the order A, B, C, or I can put them in this order, A, C, B, or BAC, or BCA, or CAB, or CBA. No matter which way I write them, they're all the same set. I generally choose to write them as much as possible in some order that makes it possible, makes it easy to see not just what's in the set, but also what's not in the set. So with individuals, I use alphabetical order. And I use some systematic order for ordered pairs, triples, sets of sets. A set can contain other sets. Okay, here we have a set that contains the set that contains A. The set that contains A is a member of that set. You look inside the outside brackets here and you will find that set right here. The set containing A, this same set, is also a member of this set. In particular, it's right here. Okay. Once you allow sets to contain sets, it makes things a little bit confusing and you have to be careful. So I'll give you a caution and I'll give you examples of things that don't work that look like maybe they should. So here we have a set that contains A. Here we have a set that contains a set that contains A and B. This set is not a member, and I use this for not a member. It's the members set, membership sign with a slash through it, is not a member of this set. If you look inside this the outside brackets here, you will not find this. The only thing you find is this, the set containing A and B, and that's a different thing from that. Those are not the same. That one people get pretty easily, okay? A little bit more confusing is here. Here we have an individual A, and here we have a set. And if you look inside that set, somewhere you can see that individual. You can see him here and here. But this individual A is not a member of this set. And the reason is that when we think of sets, when we look at sets, sets come kind of with levels, if you were. Inside of this set, we have our first level of elements, members. This is a member, and this is a member. That is, this whole set contains only 2 objects. The set containing A is one of those. And the set containing A and B is the other one. Neither of those is the individual A, and therefore the individual A is not a member of that big set. To find A over here, you don't just go inside the first level. Going inside the first level gets to this. You have to go inside of that a second time to get to A, and that makes that doesn't make A a member of the big set. Another one, here we have the set containing A, and here we have that exact same set. This set is not a member of itself. And that follows our explanation from before. If we look inside of this set, the only thing we find is an individual, not a set. And this individual is not this set. So this set is not in this set. Okay, that's the basics of sets and membership. The next thing I want to do is give 5 ways of describing sets. In semantics, we use all 5. One of them is very informal. One of them is very formal. 2 of them are very formal. And 2 of them are kind of a mix of very formal and informal. So the informal one is just using English. We say the set of all kings. Straightforward way of describing a set, and you know what's in it. King John I is in it. Chris Tancredi is not. I have never been a king. I will never be a king. I am not in that set. Or we can describe it using set theory. And the set theory is very useful in many cases. We will have to get used to this as a way of describing sets. And I have 2 different ways of doing it. One is here. It's read as follows. The set of all x, such that x is a member of the denotation of the predicate logic predicate king. The set of all x such that x is a member of the denotation of king. The denotation of king, this, itself already is a set. It's a set of all kings, okay? So we could describe that set just using it alone. The denotation of king, that is exactly the same as this set. It's exactly the same as this informally described set, okay? This one is informal, these 2 are formal, following our using our set theory. In addition to these, we have 2, again, informal ways of describing. They're informal because they're mixing in something with set theory that's not really officially part of set theory. The first one mixes set theory with English. This part, the set of all x such that x, that's the set theory. But this is just English, is a king. Okay, this is kind of an incorrect way of describing the set of all kings, but it's one way that we do describe that set. Why is it incorrect? Well, because the kind of thing that can combine with an English expression is another English expression. And if we combine an English expression here, we'd end up with an English sentence. And set theory would then not tell us anything about the members of that set. It would say, maybe King John is a king. That gives you an English sentence, but the English sentence is an English sentence, and we don't want an English sentence in this place. We want to know an individual that satisfies, that is a member of a set, and we don't really have that here. But still, we're going to use that to describe the set of kings, the same way that we use the formally correct versions from set theory. Another thing we commonly do is we mix set theory and logic. Here we have the set of all x such that logical predicate king applies to x as a term of logic. So this is part of our predicate logic. This is part of our set theory. And again, it's not really a proper way to describe the set, but it's sometimes a useful way to be able to describe a set. And we're going to use it too. It's a set of all x such that x is the king. We're going to use them both now informally to describe the sets that we want to refer to. Okay, so that's it. We've now looked inside of propositions. We've looked inside of propositions. Okay, that's it. We've now looked inside of propositions, in particular propositions that are made up of predicates and arguments, to see how they can go together and how we can give predicate logic translations to English sentences that have those that form. We take the main predicate to translate as a predicate of predicate logic. We translate the names usually as terms, but we gave more variety of possible translations for prepositional phrases. Prepositional phrases involve introducing terms that will give us location, terms that will give us paths as variables, and then give us more description about those variables that get put together with what the denotation of the main predicate is in these cases.